Hello everyone. Today I'll present our CVPR 2026 paper, Similarity-as-Evidence, Calibrating Overconfident VLMs for Interpretable and Label-Efficient Medical Active Learning. Medical image annotation requires domain experts and is extremely costly. A single CT or MRI annotation can take 10 to 30 minutes. Active learning addresses this by letting the model select the most informative samples for labeling. However, early rounds face a cold start problem. With very few labeled samples, model predictions are unreliable and acquisition functions fail. Vision language models offer zero-shot capability to mitigate this, but they suffer from severe overconfidence due to temperature-scaled softmax, which misleads sample selection and wastes the annotation budget. Let's examine existing approaches. Traditional methods like entropy, badge, and corset rely on trained model predictions. They fail during cold start. VLM-assisted approaches like PCB use softmax probabilities directly, but these are severely overconfident and cannot distinguish lack of evidence from conflicting evidence. Biomed clip, despite strong medical domain performance, still requires additional evidence calibration. Our key insight is, high similarity does not imply certainty, total evidence also matters. We address three limitations with three solutions. First, the SAE framework reinterprets similarities as Dirichlet evidence. Second, the SEH module calibrates true uncertainty through evidence strength prediction. Third, our dual-factor strategy decomposes uncertainty into vacuity and dissonance for targeted sampling. Our first innovation reinterprets VLM similarity scores as Dirichlet evidence parameters. Instead of passing similarities through softmax to get a single probability vector, we parameterize a Dirichlet distribution. The key formula is alpha k equals lambda times softmax of similarity, plus 1. Here, lambda represents total evidence strength. Think of it this way, softmax tells you how votes are distributed, but lambda tells you how many people voted. The same 70-30 split means very different things with 10 voters versus 10,000 voters. Our second innovation is the Similarity Evidence Head, or SEH module. It predicts the evidence strength lambda for each sample. SEH takes image features and the similarity vector as inputs, fuses them through a dual-branch MLP with soft plus activation, and outputs a positive lambda value. The training uses two losses. LDiff ensures lambda matches classification difficulty, and L-entropy keeps lambda consistent with the VLM's original predictions. Crucially, SEH does not modify any VLM parameters, it's fully plug-and-play. Our third innovation decomposes uncertainty into two types from the calibrated Dirichlet distribution. Vacuity measures lack of evidence, corresponding to rare cases the model has never seen. Dissonance measures conflicting evidence, corresponding to boundary samples between classes. Our sampling score combines both with dynamic weights. Early rounds prioritize vacuity for class coverage, while later rounds shift to dissonance for boundary refinement. The weights change linearly across rounds with no manual tuning. Here's the complete pipeline. Frozen Biomed clip encodes images and text, producing similarity vectors. SEH calibrates evidence strength. This parameterizes a Dirichlet distribution, from which we extract vacuity and dissonance scores for dynamic sampling. The entire process adds only a lightweight head on top of the frozen VLM. We evaluated on 10 public medical imaging datasets covering 9 different organs. SAE achieves 82.57% macro-averaged accuracy, outperforms the strongest baseline by 4.87 percentage points, and ranks first on all 10 datasets. This figure shows performance curves across active learning rounds. SAE consistently outperforms all baselines at the same 20% label budget. The gap is especially pronounced in early rounds, which is exactly where cold start methods matter most. Focusing on early round behavior, SAE maintains the lowest and most stable loss profile from the very first epoch. By contrast, badge suffers from slow convergence, and Biomed Clip plus badge shows high volatility throughout. Beyond accuracy, our model demonstrates superior calibration. On expected calibration error, SAE achieves 0.021, meaning only 2% deviation between stated confidence and actual accuracy. On negative log likelihood, SAE scores 0.425, far better than PCB and badge. The reliability diagram confirms SAE is closest to the perfect calibration diagonal. This proves our Dirichlet modeling fundamentally improves probability generation. The ablation study shows clear contributions from each module. Starting from a random baseline at 73%, dual-factor sampling adds 3.6%, VLM evidence adds 2.3%, and SEH calibration adds 3.5%, the largest single gain. This confirms evidence strength calibration is the key to our performance leap. Finally, the feature visualizations show that SAE's heat maps produce highly focused activations aligned with pathological regions. In contrast, PCB's attention is scattered, often focusing on a relevant background. This confirms that better calibration leads to better feature learning, not just better sample selection. To summarize, we introduced the SAE framework establishing a principled connection between VLM similarity and evidential uncertainty. We propose the SEH module and dual-factor strategy that decomposes uncertainty into vacuity and dissonance for transparent sample selection. Extensive experiments on 10 medical datasets demonstrate superior accuracy, calibration, and early round stability under the same labeling budget. Thank you for watching.